Hello everyone. So let's begin our regular webinar session on vector symbolic architectures and hyperdimensional computing. So today's talk is about vector quantization and the classification in randomized neural networks, to be presented by Cameron Diao from Rice University in USA. So without any further delay, I leave the floor to you, Cameron, and I will mute myself, please.
Cool. Thanks for the introduction and happy to see everyone here. I'm Cameron. I'm a junior at Rice, and this is kind of the product of a lot of my research at the Oshawson lab, specifically when I was supervised by Dr. Kleiko, who's been an amazing mentor. And so the work that I will be presenting today is on generalized learning vector quantization and classification in randomized neural networks and hyperdimensional computing. And so this is joint work that was done with Dr. Kleiko, but also Jan Emmerby and Bruno Oshawson. Cool. So machine learning algorithms are being deployed increasingly often on edge devices or devices that are located at the edge of the network and not at cloud centers. And so examples of this trend are shown in the figure. And just to point out a few, these include smart cars, health monitors, and wearable devices. And so this trend kind of attests to the many advantages of edge computing, which include lower latency, higher security and privacy, and more. However, edge devices often have significant resource constraints, and so algorithms deployed on these devices must be resource efficient. So there are several neural net architectures that meet the resource constraints of edge computing, and one of the most popular ones is randomized neural nets. So the distinguishing feature of randomized neural nets is that they randomly initialize a subset of their network weights prior to training. Thus, they typically have shorter training times, simpler optimization procedures, less model complexity, and more attractive properties. And so these properties make random neural nets an attractive candidate for edge computing applications. And so today we will be focusing on a specific randomized neural net called the Random Vector Functional Link Network, or RVFL network. So the conventional RVFL is a shallow feed-forward network comprised of 3 layers: the input, hidden, and output layers. You might also know this network under the name Extreme Learning Machine. So connections to the hidden layer are assigned random weights and biases prior to training. So training the network only involves training the connections to the output layer, which is easily solvable as a convex optimization problem. This can be done in one analytic step by solving the ridge regression problem. By finding the closed form solution to least squares of the ridge penalty, specifically, which is shown in the equation here, where lambda is the ridge penalty hyperparameter and W out is the matrix of least squares coefficients. H is the matrix of activation vectors stacked row-wise, and Y is the matrix of one-hot encodings for the class labels stacked row-wise. So after training, let's suppose that the network receives some query vector X, and we wish to classify X as belonging to one of L classes. The random network connections first perform a kind of nonlinear transformation on X to get hidden activations H. And in the first equation here, Wn would denote the weight matrix of the random connections, while B denotes the hidden layer biases. And then G denotes a nonlinear activation function, typically the sigmoid. And then after that, the trained connections transform H to get a vector Y of length L, where each component of Y corresponds to the activations of distinct classes. And so then we classify X as belonging to the class whose component in Y has the highest activation. And you might also know this classification strategy under the overall term of one versus all classification. So we will now discuss a form of RVFL network called GLVQ-RVFL. So the GLVQ-RVFL network was motivated by key insights from 3 different fields. First, from RVFL, the network retains the basic features of an RVFL network. Second, from hyperdimensional computing, the network projects the input features to a hyperdimensional space prior to training, which is a hyperdimensional computing operation. And then third, from learning vector quantization, the network trains network weights using a learning vector quantization classifier. And if some of these terms seem like unrecognizable or like unknown, I will be getting to very shortly. So in a conventional RVFL, the random connections kind of project the input data to a high dimensional activation space. And this activation space is reminiscent of the representational space in hyperdimensional computing, or HDC. And so we list here just some of the basic ingredients of any HDC framework. As I just alluded to, the framework includes a representational space for the input data. The space must be very high dimensional, on the order of 100 to 10,000 dimensions, and hyperdimensional or HD vectors are drawn from the space to represent their respective input data samples. These HD vectors are drawn randomly so that by construction, any 2 HD vectors have an extremely high probability of being quasi-orthogonal. We can measure similarity between HD vectors using a similarity metric, such as Hamming distance or cosine similarity. We can also perform certain relational operations on HD vectors, such as variable binding or bundling. And these operations let us construct relational objects from HD vectors, objects that include things like sets, sequences, predicate relations, hierarchies, and much more. And so now returning to the conventional RVFL, if you recall, we fix random connections to the hidden layer before training. And so we can actually use these random connections to project the input data to hyperdimensional space. This idea was proposed by Kleiko et al. And implemented in their network called intRVFL. And I included a citation of where they introduced this network at the bottom. So they add a representation layer prior to the hidden layer that encodes the original features with thermometer codes. And specifically, the layer quantizes the input features using the first equation here, where xi denotes the ith feature value and n denotes the number of hidden layer nodes. Then the layer encodes the quantized feature values as bipolar vectors with v as the density of ones in each vector. And so you can better visualize the encodings in the diagram on the right, where each column is a distinct encoding vector, and the green nodes represent ones and the red nodes represent negative ones. So after the encoding process is complete, the network fixes connections to the hidden layer using a weight matrix Wn that is random and bipolar. The network computes activations in the hidden layer by binding the encoding vectors with the bipolar vectors comprising Wn, in our case with the Hadamard product. And these activations are used as inputs to the clipping function, which serves as our nonlinear activation function. And you can see exactly what the clipping function does on the bottom right, where it basically just clips the magnitude of each of the activation values. So the binding of the encoding vectors with Wn is what projects the input features to a hyperdimensional activation space. And this projection is shown in the network diagram as the fixed random connections. And once the input features are projected, we train a least squares classifier on the resultant activations. And the weights of the least squares classifier are stored in readout matrix WL, which we encountered before. So we, of course, want to evaluate the changes to RVFL we've discussed so far, and we'll be examining some relevant experiments testing how the changes impact RVFL performance. So these experiments were all run on 121 datasets for classification from the UCI machine learning repository. Here we show some of the statistics summarizing the data sets, just like describing the number of examples, number of features, number of classes. You can see that they vary quite widely. And so in all experiments, the data was pre-processed by normalizing features to the 0-1 range. And this is the only pre-processing step. And Delgado et al. Were actually the first authors to introduce these data sets as a benchmark for classification accuracy. And they reported that the highest accuracy they obtained on the data sets was 0.82 by random forest. And so for comparison, the average accuracy of the linear least squares classifier was 0.73. And from now on, I'll be referring to the linear least squares classifier as just the RLS classifier, or regularized least squares. Cool, so we first conducted an experiment comparing the conventional RVFL and intRVFL networks. This experiment was meant to evaluate the effectiveness of projecting input features to an HD activation space before training. Accuracies for both networks were averaged over 5 independent runs on the data sets. So we found that the mean accuracy of the conventional RVFL was 0.76. Meanwhile, the mean accuracy of intRVFL was 0.80, and results for both networks were highly correlated. So the higher accuracy of intRVFL kind of gives support to the proposed method of deriving activations as HD vectors. So I just want to highlight some connections between the projection method of intRVFL we just talked about and conventional projection methods in HDC. So in particular, the method used in intRVFL is almost entirely similar to the record-based encoding used in HDC. So in record-based encoding, a feature vector has each of its n feature values quantized to d different levels. Then the quantized feature values are encoded as d-level hypervectors, which are not necessarily quasi-orthogonal to each other. So in the diagram, the level hypervectors are shown as these vertical plotted lines, and their heights represent the levels of their respective feature values. And you can see the levels kind of marked off on the y-axis, ranging from f-min to f-max. In our case, I'll get into that shortly. But next, we randomly generate n position hypervectors that are quasi-orthogonal to each other, and we bind these position hypervectors with the level hypervectors we generated earlier. This binding gives us n HD vectors that represent the n original feature values. And then finally, we bundle these HD vectors into a single projection vector H, which represents the original feature vector projected to HD space. Since bundling preserves similarity, H kind of retains the feature value information of the original feature vector. So now if we go back to the intRVFL projection method, we can kind of see the similarities it has with record-based encoding, and they become more apparent. So both methods quantize and encode feature values, where intRVFL specifically encodes them as bipolar vectors. Both methods also bind the encoding vectors with randomly generated position hypervectors. In intRVFL, these position hypervectors comprise the random matrix Wn. And lastly, both methods bundle the HD bindings together to form a single HD vector H. In intRVFL, H is just the activation values of the original feature vector. So we just discussed a general way of projecting data to HD space, but then we might ask, how would we classify that projected data? And a very simple way of doing so would be by using a sort of naive HDC classifier. So this HDC classifier forms class prototypes from HD vectors of the same class. And this means bundling the vectors so that the class prototypes are similar to their example vectors. We can then store these class prototypes in an associative memory, as seen in the diagram on the right. And once we're given a new query vector or test vector X, we can classify X by encoding, or I've been saying projecting it to HD space and then measuring its similarity to the stored class prototypes. And then X belongs to the class whose prototype is most similar to X's projection vector. So the HDC classifier can be quite attractive for its simplicity. It requires no training and only enough memory to store a single prototype per class. And HDC classifiers in general are suited for edge computing environments because of their ability to run on parallel architectures. In addition, several FPGA accelerated and ultra-low power implementations of HDC classification have been proposed. However, this HDC classifier we just introduced can suffer from certain issues. In particular, any one class prototype representing a large number of HD vectors may fail to capture intra-class variability. And also, while class prototypes capture major similarity among hypervectors of the same class, they could fail to capture hypervector differences between classes. And so we can run experiments to examine the performance of the HDC classifier more concretely. So Rosado et al. Ran an experiment comparing the RLS and HDC classifiers on the UCI datasets. Both classifiers were trained on the activations of intRVFL, and accuracies were averaged over 10 independent runs on the datasets. So they found that the mean accuracy of the RLS classifier was 0.80. And meanwhile, the mean accuracy of the HDC classifier was 0.70. The results for both classifiers were highly correlated. However, the RLS classifier has significantly higher accuracy than the HDC classifier when training the readout weights of intRVFL. So now, instead of classification accuracy, we take a look at the computational cost of the RLS classifier. We saw that the classifier performs a number of matrix operations, including a matrix inversion that drives the cost of the classifier. And so it was in the least squares, the closed form version of the least squares equation, it was just H transpose H plus lambda I inverse. And this matrix inversion typically places a high computational burden on hardware implementations and may cause numerical instabilities. We can somewhat resolve these issues by using matrix decomposition methods or by computing the Moore-Penrose pseudo-inverse instead of the inverse directly, since computations for these methods can be parallelized using GPU clusters and are typically more stable than just computing the inverse straight away. However, these methods would then rely on specific hardware resources, which would restrict the type of resource-constrained devices capable of training RVFL networks. The HDC classifier avoids this problem since it only really relies on simple distance calculations and vector bundlings. So in general, for the intRVFL, we would like a classifier that avoids complex matrix operations like the HDC classifier, but ideally, this classifier should have accuracy comparable to the RLS classifier in order to preserve the performance of the overall RVFL network. So several researchers have devised HDC learning rules to improve the accuracy of the HDC classifier. And the learning rules just adapt class prototypes to find decision boundaries in HD space that better approximate Bayesian borders. And so we show 3 of these learning rules here. As you can see, they're quite similar to each other, as well as to the perceptron learning rule. And specifically, they just, for all of them given like a query vector, like training vector H or Q, they just adapt the 2 closest prototypes based on the query vector. And so specifically, it would be the closest prototype sharing the correct class label and the closest prototype sharing the incorrect class label. And you can see that like the notation is different, but this is the general thrust behind all of these learning rules. Now, I want to introduce learning vector quantization, or LVQ, as a different class of learning rules used to kind of train class prototypes. And LVQ classifiers learn prototypes using a winner-takes-all Hebbian learning approach. Thus, these classifiers are typically simple and fast. In particular, the computational cost of LVQ training scales linearly with the size of the training set, while the cost of classification depends only on the fixed number of prototypes and the input dimensionality. So at first glance, LVQ classifiers seem to be an attractive candidate for training the readout weights of intRVFL. I want to point out some connections between the LVQ and LVQ learning rules and the learning rules we talked about earlier. So on the right, you can see the original sort of LVQ learning rule devised by Conan. And W plus is the closest prototype to query vector X with the correct class label, and W minus is the closest prototype with the incorrect class label. Upon closer examination, we can see that the LVQ learning rule is very similar to the perceptron learning rule. The only difference is that the LVQ learning rule really updates the class prototypes based on the distance of the prototype from query vector X, while the perceptron learning rule, I believe, updates prototypes with X itself. The result is that the LVQ learning rule updates W plus and W minus by attractive and repulsive forces from X, respectively. And you can kind of see this process visualized here. So the perceptron and LVQ learning rules are actually heuristic, usually, and subject to slow convergence and instabilities on specific patterns of data. And since both learning rules are so similar to the HDC learning rules, we believe the HDC learning rules could potentially suffer the same difficulties. So returning to the intRVFL architecture, we want to use a different learning rule to train our projected HD vectors in activation space. We chose generalized LVQ or GLVQ for its generalization error bounds and fast convergence guarantees. So right now I won't explain how these guarantees are proven, just so I don't muck through the theoretical details, but you can find proofs or directions to the proofs in the papers that I have cited below. So just as with LVQ, the GLVQ classifier consists of prototypes. The prototypes are learned iteratively using the GLVQ learning rule, which is kind of formalized on the right here. Here, the relative distance difference is a quantity determined by the distance of the query vector from its closest prototype with the incorrect and correct class labels. And we typically use squared Euclidean distance as the distance metric for GLVQ, which is closely tied to the dot product commonly used in HDC. And then on the bottom right is a diagram that visualizes how the GLVQ learning rule updates W plus and W minus with attractive and repulsive forces from the query vector, respectively. So as a final note, so far I've assumed that we represent each class with one prototype, and we have to represent each class with at least one prototype, but we can adjust the number of prototypes per class as a parameter of our classifier. And so this allows us to better capture intra-class variability among data samples, which you might remember is a problem that I pointed out might potentially apply to HDC classifiers. It also allows us to better approximate Bayesian borders, because now we can form these kind of piecewise decision boundaries. So in sum, we treat the readout weights of the GLVQ-RVFL as prototype weight vectors for classification. GLVQ-RVFL trains these readout weights using a GLVQ classifier instead of the RLS classifier commonly used in RVFL networks. And so examining the GLVQ-RVFL architecture I displayed on the screen, we find that the GLVQ-RVFL actually acts as an HDC classifier, since it projects the input data to hyperdimensional space and then trains a prototype-based classifier on the resultant kind of class prototypes we form from the HD vectors. So we conducted our own experiments to compare the RLS and GLVQ classifiers. In one experiment, we trained both classifiers on just the normalized input features and restricted the GLVQ classifier to only one prototype per class. Accuracies for both classifiers were averaged over 5 independent runs on the datasets. So I mentioned earlier that the mean accuracy of the RLS classifier was 0.73. Meanwhile, the mean accuracy of the GLVQ classifier was 0.76. Results for both classifiers were highly correlated. We hypothesized that this is because both classifiers have linear decision boundaries, and so both can accurately classify linearly separable data, but exhibit different behaviors when classifying non-linearly separable data. And so in this next experiment, we trained the RLS and GLVQ classifiers on the activations of the conventional RVFL. And so we confirmed Kleiko et al.'s finding that the mean accuracy of this RLS classifier was 0.76. And the mean accuracy of the GLVQ classifier was also 0.76. So again, results for both classifiers were highly correlated. I included this experiment to demonstrate how both classifiers have similar performances, even though they can behave sort of differently on certain data sets, as shown on in the plot on the right here. So in this experiment, we trained the RLS and GLVQ classifiers on the activations of intRVFL. And so this experiment really introduces the performance of GLVQ-RVFL. The point of this experiment, more specifically, was to evaluate how well GLVQ could distinguish classes in a sort of resource-constrained environment. So GLVQ is once again restricted to only one prototype per class. We found that the mean accuracy of the RLS classifier was 0.80, and meanwhile, the mean accuracy of the GLVQ classifier was 0.81. We also tried severely limiting the number of training iterations for the GLVQ classifier to just 10 iterations. And then GLVQ had a mean accuracy of 0.80. So this is the same accuracy as the RLS classifier. In general, the hyperparameters for the GLVQ classifier can be adjusted to achieve different levels of efficiency. And this flexibility is not typically available when using RLS. So if you recall, we chose GLVQ to train the readout weights of intRVFL, in part because we wanted to avoid some of the expensive matrix operations of RLS. So we wanted to compare the computational costs of the RLS and GLVQ classifiers on the UCI datasets measured in flops. We used two different approaches to compute the least squares weights of the RLS classifier. The first approach, which is on the far left of the table here, we called it RLS straightforward. So it computes weights using the Moore-Penrose pseudo-inverse. And the second approach uses QR factorization to decompose the matrix inverse. And we chose QR factorization as our decomposition method, since it seems to be the most popular method for computing the readout weights of a RVFL in a cost-efficient manner. And this was reported in Valena et al.'s survey on hardware implementations of RVFL. We note that GLVQ differs markedly from the two approaches to RLS, since the cost of the GLVQ classifier is driven by the number of distance calculations and the number of training iterations. And so you can see this more clearly in the table on the far right, where unlike RLS, GLVQ depends on P, the number of prototypes per class, and I, the number of iterations. So we found that the RLS classifier employing QR factorization had 79% of the computational cost of the straightforward RLS. And just in full disclosure, QR decomposition can actually be implemented with a variety of methods like Gram-Schmidt orthogonalization and such. So we chose householder reflections. This was also mentioned in Valena et al.'s survey. And then meanwhile, the GLVQ classifier had only 21% of the computational cost of the straightforward RLS and achieved the same accuracy. Thus, GLVQ-RVFL can provide a more cost-effective method for training the readout connections in an RVFL network than RLS. So if you recall, I said earlier that we can adjust the number of prototypes per class for the GLVQ classifier. And in the previous experiment, we restricted the GLVQ classifier to only one prototype per class to reduce computational costs. But we also wanted to evaluate the full potential of GLVQ-RVFL. So in this experiment, we compared the RLS classifier to the GLVQ classifier with multiple prototypes per class. And we expected better performance from GLVQ-RVFL because, as I mentioned earlier, multiple prototypes per class ideally would allow you to better approximate nonlinear decision boundaries, or nonlinear, I guess, Bayesian borders. And so this experiment also demonstrates the full viability of GLVQ as an HDC learning rule. Once more, we pass the activations of intRVFL to both classifiers as input. You might recall that the mean accuracy of the RLS classifier was 0.80, whereas the mean accuracy of the GLVQ classifier this time was 0.82. And as I mentioned before, this is the highest accuracy previously obtained by Delgado et al. On the datasets. Results for both classifiers were once again highly correlated. And finally, we severely limited the number of training iterations for the GLVQ classifier and obtained a mean accuracy of 0.81. The final experiment we conducted was to compare GLVQ-RVFL with kernelized GLVQ. So the kernelized GLVQ adopts a similar classification strategy as compared to GLVQ-RVFL. It essentially projects the input features to some kernel space before learning prototypes in that space. And specifically, the classifier adopts the GLVQ learning rule, but with kernel distances instead of the squared Euclidean distance metric that we used. In practice, the use of KGLVQ is computationally kind of prohibitive in edge computing applications because of the large costs associated with computing the kernel matrix and the kernel distances. But we still conducted this experiment because of the similarities I mentioned between KGLVQ and GLVQ-RVFL. We wanted to measure GLVQ-RVFL against an already existing method for projecting then classifying input features using prototypes. And the kernel we used for KGLVQ was the popular Gaussian kernel. So both classifiers were limited to 2000 iterations. And we found that the mean accuracy for KGLVQ was 0.79. So KGLVQ had worse classification accuracy than GLVQ-RVFL, which had an accuracy of 0.82. But note the extremely high correlation between the results, which would kind of suggest similar classification behavior. And in this slide, I'm just, in the interest of full disclosure, I attached a link to the code I used for my training and testing procedures for all of these experiments. And so I have the link here, but I can drop it in the chat. So training was performed with the SciPy optimized minimize library, but of course, PyTorch implementations are supported just because they offer a wider variety of optimizers you can use, like the popular Atom optimizer or SGD with momentum. And finally, I just wanted to give special thanks to the ProtoTorch and scikit-learn LVQ libraries for their LVQ implementations, which were very intuitive and simple to use, and allowed me to kind of implement my experiments in both the SciPy and the kind of PyTorch libraries. Cool, and as final takeaways, to summarize, GLVQ-RVFL contributes to 3 fields of research. First, for RVFL, it represents an alternative method for training the readout connections of an RVFL network. Second, for HDC, it is a new HDC classifier that provides state-of-the-art accuracy on the UCI datasets. And third, for GLVQ, it provides a simple nonlinear transformation of the original features that the GLVQ classifier can leverage for higher accuracy. Overall, we believe that our proposed GLVQ modification can flexibly improve the accuracy and efficiency of RVFL networks run on resource-constrained devices. Thus, it expands the network's range of potential applications to edge computing. And before I open up for questions, I just wanted to give some final acknowledgements. I wanted to thank Dr. Kleiko for being an amazing mentor, especially not just the summer, but over the school year, and really guiding me through the research process and through all these experiments and such. I also wanted to thank Jan and Rabai and Bruno Schausen, of course, for a lot of their really helpful, constructive feedbacks and for being really welcoming to the lab. And yeah, so now I'm willing to take questions, and thank you guys for listening to my presentation.
Thank you very much. really exciting to see this kind of improvement. So let's start the discussion session. So anybody, turn on your mic, shoot a question.
I'm interested to know what weight scheme you guys used for the training, like what types of weights rather in terms of the representation.
Are you talking specifically about the weights of the random connections or the ones connecting to the output layer?
Both.
Oh, okay. Yeah, for sure. So the one that was the weights of the connections to the hidden layer. So these are the random ones. These, it was just a bipolar matrix. So it was just a matrix of ones and negative ones. And then the weights of the connected to the output layer, these were not restricted to just like integers. So these were just your regular like real value numbers and stuff like that, if that makes sense.
Okay, thank you. Oh, sorry.
Oh, no, you're good.
That was, yeah, I was wondering whether, and so for training, did you guys like enforce the restriction that they be either 1 or -1 as well? Or did you allow intermediate values during training for the randomized layers?
Yeah, so for the randomized layers, we kind of enforced it so that everything was kind of like integer only. So if you recall, like, you know, the random matrix itself was full of ones and negative ones. The density, the kind of encoding vectors that I talked about were also bipolar vectors. And so if you perform all these like vector additions and vector bundlings and stuff like that, the result is still like integers. And so the end result is that all the activation vectors are going to all be integers as well.
Okay, awesome. Thank you.
Yeah, no problem.
More questions?
Perhaps I can ask one or maybe two. Yeah, really interesting talk. I was wondering if you could elaborate on how you choose the optimal number of the prototypes, and perhaps if you have seen any sign of overfitting by increasing the number of prototypes.
Yeah, for sure. So yeah, I should have mentioned this at the end, but the method or procedure we used for finding optimal hyperparameters, which is grid search. And so we ranged the number of prototypes per class between 1 and 5. And then we just ran experiments to see which one fit for certain data sets for every data set. And then as for overfitting, yes, I think especially like diving into the literature, there was like a number of papers which found that it's kind of like a balance between using more versus less prototypes. More prototypes can allow you to like fit nonlinear decision boundaries, but of course, it does lead to overfitting, which is why we use grid search to find the optimal number for like each data set, if that makes sense.
Yeah, thank you.
Yeah, no problem.
Ambas, you said you had 2 questions.
Yeah, okay, I can yeah, so it is just a very traditional question in terms of the comparisons. I recall that at the beginning you pointed to the data set, and if I recall, it was a random forest, one of the kind of competitive baselines that they established for this data set. So I was wondering if you have tried to do a comparisons with the, let's say, the trainable part for the random projections, right? But giving the network the same number of, let's say, parameter, and then see if end-to-end training of the readout plus the projections perhaps could give a significant boost, or this is already close to what you have achieved. I guess that would be really a strong baseline, because especially nowadays we have off-the-shelf method that you could also quantize the weights in the projection as well as the readout. So essentially, you know, our competitive part is also getting very close to operate with, let's say, low bit width precision. Yeah, I know that is totally different scheme, especially you guys try to reduce the, you know, the number of the iterations and, you know, make it as much as possible computationally efficient. But I was just wondering if there is a comparison with the kind of end-to-end training of the both layers, or how far they could get better than RF baseline.
Got you. Yeah. So we mainly just pulled it, mentioned random forest as just like, this is the highest like state-of-the-art accuracy. I agree. I think that an experiment kind of comparing the two, one of them off the shelf and then one of them as this like end-to-end training, like projection and stuff like that, would be pretty helpful. And I think I will maybe see if I can like test it out, but I think that, yeah, but the way we did it was that we didn't actually perform like a direct experiment comparing the two. We just like pulled the result and used it as like a comparison to see exactly what does it mean for GLVQ-RVFL to have like 0.82 accuracy.
Yeah, excellent, yeah.
Mm-hmm.
Very nice. More questions to Cameron? More reflections. HD vectors or VSA in machine learning context. So do we have, well, what kind of future can we expect? Any reflections on this topic are welcome.
Yeah, I'm glad to see that something's better than perceptron is getting there. It's interesting, yeah.
Yeah. I also personally I found it very appealing that the entire pipeline was expressed in terms of hypervectors. So because originally with the intRVFL, so this the traditional part that was left, I mean, it was a little bit bothering. So that's kind of combination. But you know, with this addition, it's kind of sounds very logical to have this classifier at the end.
Yeah, indeed interesting. Yeah.
What's strange is that all the ingredients were basically there, and I must say that we kind of, I mean, somehow, like you wouldn't see learning vector quantization as sort of the standard component of a machine learning course or textbook. So we just came across this area almost by a chance, I would say. And then once you start to read about learning vector quantization, you see that they operate with this term prototype, exactly the same term we used to use in HD computing. And then we just realized that, oh wow, it looks like, you know, it should fit very well, like what we are doing, just because it can be seen as just something on top of the, because like in learning vector quantization, like this forming centroids is exactly the most common way to initialize your prototypes. Just that's kind of the very first step everyone does there. And then on top of it, I mean, there are like lots of different versions of LVQ algorithms. There are even like extensions on top of the GLVQ, like kernel ones. So Cameron has mentioned this one. There are also ones where you also have an additional covariance matrix between different components of your vectors and so on and so forth. So people have been like studying this field for like a couple of decades, almost 3 decades. But somehow now it's like relatively rare, you know, to hear about it. Even though it seems to be of a very good match, at least for extending what we are doing with classification problems within HD computing context.
Talking about kernel-based version of your classifier, so Abbas can help me, I mean, with the proper name of this method. So what you are currently suggesting is actually so applying kernel function to the original feature vectors, right? But then, I mean, there are ways to kind of generate the vectors, so not to encode, but I mean, for a given kind of raw input, so you would generate vectors which would approximate some kernel function on the raw data. That's so now Abbas should tell me if I'm correct or not. So what? So it was one of your methods,
yes,
right?
It is getting to that direction. Yeah.
Yeah. So that would what I'm thinking is that I mean, converting to HD I mean, maybe the proper way of converting to HD, it should approximate kernel computation. So you don't need to first compute the kernel and then to convert it to HD. So maybe
the funny thing, Evgeny, is I recently realized that the intRVFL projection, like the projection with thermometer code, it in fact does it. This is the funny thing.
Yeah, but I mean,
like,
exactly.
If you plot the similarities between different values which you create with the thermometer code, you actually end up with something which reminds of a triangular kernel. Like effectively, this is like thermometer code effectively imposes a triangular kernel on your data. And that's likely the case why it works better than the standard projection used in conventional VFL. Like a VFL, when you use TNH function as a nonlinearity or sigmoid function,
exactly,
it doesn't impose any kernel. Like there is no
kernel. Of course.
While like, if the introduction of the thermometer code, it imposes something which it's not exactly the kernel, but it's extremely similar to kernel.
That's what I think it would be interesting to kind of systematize. I mean, so I remember this, I mean, kind of keywords on or kind of key problems of HD. So coming even from Pentis papers and book, the encoding problems. So the encoding into HD should allow for this classifiability in HD space. So also connecting to what was presented earlier before on the theoretical side.
Right. You know, and Fritz is going to give a talk about like how to form actually kernels. Like we have this recent preprint, like which is from last week, effectively, and that preprint talks exactly about how to form kernels of like, you know, of a way, like of an extreme amount of different shapes. You pretty much, you can choose, I mean, with some limitations, you can choose the shape of the kernel you would like to represent with your high dimensional vectors. So the only difference is that the method Fritz is going to talk about, it assumes, well, either real valued or
Well, I think Zoom decided that it was too much of spoiling future talk of Fritz, and they froze Dennis in the middle of the sentence. But yeah, but I guess we will hear the details in Fritz talk in a few weeks. In the meantime, so do you hear me, by the way? Or am I also? Yeah, okay, cool. I just want to quickly share my screen. And I want to so VSA, yes. So go to our beautiful website showing the program for the, well, still summer session. So we have several talks to go. So next talk, so you see, so the agenda is pretty much, or slots are occupied, some fields are to be filled, but saying this, so please insert in your calendar these events. This is the first message. And secondly, now I'm soliciting talks for the winter session already, which will start after the Christmas break. So please feel free to contact me. I really look forward to your contributions and your presentations at this webinar series. Yes, but so let's see. So Dennis has disappeared completely. So let's, unless we have any more questions, so let me ask again. So are there any more questions? well, if no, then I finish this webinar. So see you in 2 weeks. So thank you for today.
Thank you.
Thank you.
Thank you. Thank you, guys. Bye-bye.
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 Thanks a lot.
Bye.